Okay, hi everyone. My name is Alexandre. I'm a PhD candidate here in Federal University of Rio Grande do Sul. And today I'm going to present you a work that we published an article, and it's called Fine-Tuned Robust Optimization. The main idea is to attain robustness and target ideality. It is an integration of target-rich mindset, data-driven management, and robustness. Okay, so first I will ask a question here. Is this an optimization problem? We cannot actually plan what we don't expect because it will be far from the reality in the real practice. So real life planning is about to estimate, okay? Uh, our estimation says everything. And actually, in big real problems, deterministic lack details. So here we can have an idea. And we can see here that the deterministic optimization is very far from the real life, I mean, uncertainty. So real life planning is about to optimize what we estimate because uh, of many things, and one of them is that the market is volatile. Okay, and the pandemic is a great example of that. Everything changed. Okay, so realistic problems. In realistic problems and mainly in operations research, we use actually two approaches. Either we use stochastic programming or we use robust optimization. Okay. Stochastic programming is generally used for linear problems, but you can have non-linear constraints. And it's basically this problem. Instead of just optimizing as a deterministic problem, here we include the expectance of another stage. For example, operation costs. So here we have operation costs, one stage, and facility costs, another stage. This is the most famous approach of stochastic programming. And basically this problem here, it is, uh, it is transformed in another problem to be solved then. And it is called deterministic equivalence. So it is a big linear problem here. And I will talk about the drawbacks about this methodology, and after that, I will talk about uh, the drawbacks about robust optimization. Robust optimization is actually used for linear problems, okay, convex problems. Uh, but you can use it to nonlinear problems, but it must be convex. So basically, the main idea is to maximize or minimize a deterministic problem. Here you have a stochastic problem, okay? But here you have a deterministic problem, and it can be transformed again in a linear problem, here, this one, and then you solve it. The main idea here is to find the best parameters, and it mainly a hyperspheres, okay? So here, you just have to find the best parameter value that will give you the most conservative uh, value of your objective function. This was the first approach developed by Saucer in 1973. But after that, many other approaches have appeared, but the idea is basically the same. You have to control robustness and conservatism. If you increase the robustness of your problem, you will uh, increase the conservatism of your problem. So you have to balance these two things. Uh, but how do you choose the estimation for your problem? I mean, uncertainties for your optimization. Why don't you let the machine decide? Humans are emotional. Data-driven choices are logical. How to do optimization? Humans create models that represent the real life. Machines don't have this power better than humans. We are better observers. So fine-tuned robust optimization uses the integration of machine data-driven and human to decide. What I mean is that machine data-driven precludes fictitious results and captures trends. And the human, we have the power to think and to observe. We should look to the trend. Data gives the trend to success and a better estimation. I mean, less error. So here is a resume of the method, okay? And it's mainly 3 steps. The first step, you have to adapt the model to increase the robustness of your model. So in this step, you're going to transform the old problem into a new one without destroying its constraints nature. This is very important, and I will explain further. The second step, you have to fine-tune your normal uncertainty. I called it epsilon, and the vector of penalty factors, alpha, to attain a solution closer to ideality with a specified preset trade-off risk. So again, in robust optimization, we generally make the balance between robustness and conservatism. And here in this methodology, I specified what is this trade-off that I want. So basically the problem is this one. You have to optimize your normal uncertainties and your penalty factors subject to a loop problem. And this loop problem is an optimization problem. It is a transformed deterministic problem that is subject to this preset trade-off risk and your specified target or calculated target, and subject to your constraints of the old problem. Again, we don't destroy the old problem. It must have its own nature. And the third step and the last step, you're going to stochastically optimize the problem. And it's simple. Once you have the fine-tuned parameters, I mean epsilon and your penalty factors, all of these are fine-tuned. Now you just have to make n big optimizations. I will talk about it further. And then you're going to store the final values of the optimizations, and for your decision making, you're going to return the best one, the best objective function value. So if we make a comparison between fine-tuned robust optimization and the literature, I mean, the most important and used in the literature for operations research, for example, that is the stochastic programming and the robust optimization. Here, I will begin with the literature. In the literature uses probabilistic constraints that it is hard to solve, and it generally naturally makes the model nonlinear. You're going to work with the scenarios, and the bigger the amount of scenarios, the less robust is going to be your problem. And it's really a big problem for real problems. And you calculate trade-off risk. Actually, you don't have works that you can specify your trade-off risk. Actually, you work with probabilistic constraints. The number 4 is that you're not going to see a target reach oriented with robustness control. You can see something like target reach oriented, but not with the integration with robustness control. Number 5 is that you have to use in convex, but it can be nonlinear, but it need to be convex to use these methodologies. And the number 6 is that you don't have multiple benefits by using these methods. If we look here to these 6 points, I consider that the most critical one is the first and the second. It's really critical here because it's not hard, it's not easy to solve, okay? And based on that, the idea was, first, you are going to avoid transforming a linear problem in a nonlinear one. And this is very important because, for example, if we see this simple equation here, this objective function equation here, we can see that, wait, hey, if we are optimizing epsilon, why don't I just let it be a variable? It's a big problem because actually if you let it be a variable, you are going to transform your linear problem into a nonlinear one. So we don't do this, okay? It won't make your model more robust, okay? On the other hand, it will make your problem less robust, so this is a big problem. The second point is that we control robustness as you want, okay? You're going to specify your trade-off risk, and based on that, the algorithm will force to find a configuration that make it becomes true. The third point is, this is a methodology that is target-rich oriented. Number 4, linear and nonlinear applications. You can do to both, but we're going to talk about the restrictions of it further. Number 5 is that you have some space for create your risk decisions if you want so. And number 6, that it is data-driven optimization. You can use it to short, middle, or long run planning, or whatever you call decision making, and it will give you more realistic planning. And number 7 is that it precludes ambiguity. So you don't need to use distributionally robust optimization, for example, because with this methodology, you're going to reshape your probability distribution. I will talk about it further. So here we have a graphical abstract of the framework. Basically, what it does is that you take your original model, then you apply the mathematical formulation of the framework to transform to a new one, and then you are going to adapt your model based on that. Your algorithm will have 3 inputs. The first input is a criterion. You're going to set your trade-off risk. The second input is that you're going to set a target, or you can specify it, or you can calculate it based on a new concept that I will talk further. And the third input is your original model. Actually, your transformed model. Then you are going to execute your algorithm. Okay. What the algorithm does is the following: you fine-tune the model following your preset criteria. Okay. And then you stochastically execute your fine-tuned robots optimizations. We already saw that. And after all, you're going to filter the best solution, and this is going to be your decision making. Okay. Okay. So the first step here is the mathematical formulation. Basically, it is either a minimization problem or a maximization problem. Okay. So here, what is X? X is your vector of decision variables. Epsilon is your normal uncertainties. Okay. And I will talk about that later, why it is important to have normal uncertainties in your problem and in any problem. Theta is the vector of deterministic parameters, I mean the scalars. And alpha is the vector of penalty factors. And zeta is the vector of non-normal uncertainties, other uncertainties. Okay. Subject to a normal. This is a deterministic problem, okay? So the rest is the same as any other deterministic problem. The question here is that you have to know how you are going to design your problem. You have to ask yourself this question: how can I better design my problem, including all of these uncertainties and my penalty factors? And for example, how to increase robustness without changing the model? How do we include the penalty factors in order to increase our robustness? This is the question. You are going to reshape your probability distribution, respecting its bounds. Okay. You have, for example, let's suppose it is an exponential distribution. So for the uncertainty I, following an exponential distribution, you have a lower bound and an upper bound based on your historical data, okay? You have to respect it because it must be realistic, okay? So you're just going to multiply your exponential distribution by a factor alpha, okay? It can be any probability distribution, but not a normal uncertainty, okay? Normal probability distribution, it can't be normal, okay? So here, alpha values varies within nested loops or are specified. So the default value is equal to 1, okay? So you will start with 1, and you are going to vary it, in a way that you have to respect the lower and upper bounds, okay? So how do we calculate alpha to make it more fast? We're going to talk about it later. So how do we include data-driven mindset? It is a concrete thinking mindset. If you look to neural networks, it's an abstract thinking. Here, we don't know that black box, what the black box of a neural network is doing. But here we know what we are doing, okay? It is a concrete thinking mindset. The idea is to create a decision making that gets closer to what you desire and that you consider the historical trend and pattern to not diverge from a feasible reality. So we always look to data. So how do we do that? Okay, we have to create 4 concepts, okay? So the first one is the general deterministic optimization of reference, the GDOR. This is only a guide to determine the target ideal solution if you don't specify it, okay? For example, this is important because sometimes you are going to give some data, but you as a decision maker, you cannot, for example, you may be lost and you don't know, hey, what is a ideal solution? So here you know how to calculate it. And again, I said that it has space for your risk decisions, and one space is the form that you calculate it. You can change the way of calculation, but in the article I said that a good way of calculating it is based on the average. Okay, so for example, suppose you have 2 years of data, and in these 2 years of historical data, you made 20 optimizations. Okay, 20 optimizations, 24, one per month to be precise. So each month we make a deterministic optimization in our company, and we know that for each month we have the data for that month, okay? So N is the number of months in this case, that is 24, the number of optimizations, and I is the parameter, okay? The indexed parameter. So for a parameter theta, for each parameter theta, we have data for this parameter. And since we made 24 optimizations for this parameter, now we have to sum these 24 terms, and we're going to have an average. We take this average, we put in our deterministic problem, and this is our original problem, okay, without transform it, and we have the ideal solution. It could be, okay, and again, always respecting the bounds. So I prefer to specify it. So after that, we have the recent reference timeline. This is another important concept because we are going to use both of them in the algorithm. They are bounded. They are linked with each other. So the average, what is the RRT? It is the average value of normal uncertainties used as reference to generate all X spots. And we will see next what it is. And all other deterministic parameters. And again, this is based on the average. Okay? So, okay. How to include data-driven mindset? We are going to have the historical database. I gave an example of having 24 months of database, okay? Suppose that my GDOR is the general pattern, is based on these 2 years of data and 24 months, okay? What is the recent pattern? For example, it could be last month, okay? Why do we do that? Because actually, we know how our company have been working in 2 years. We don't want to change this suddenly, okay? So how can we respect of what the company was doing, and how can we redirect our problem to a better target based on the most recent thing the company was doing? This is very important because it actually is the form how we follow the trend, and the trend never gives bad things. It's always good to follow trends. So based on these two concepts, it is possible to do it, to create a more realistic planning. And this is how we estimate our problem, okay? So it could be, for example, 2 months, 3 months. You choose what you judge it's better. Okay, so realistic planning, less mistake, I mean, is more feasible when one knows how the process behaves. So this is another argument to use this data-driven concept and this data-driven mindset, okay? And how to do it? How to include the target-rich attributes in our framework, in our algorithm? How to do it? Actually, we have 2 other concepts. One of them is called the relative regret. So here, the relative regret is just a deviation, okay? It's just a deviation based on the target ideal, the ideal solution. So here we have our calculated or specified ideal solution. We will subtract the absolute value of this in respect to our robust transformed problem. After we make the transformation to a more robust model, now we are going to optimize it based on the concept of RRT, and then we are going to subtract it. It will be a criterion for the algorithm to stop. We'll see it further. So, and the average relative regret is just the average of this, of the amount of optimizations you do to fine-tune your program, okay? For each standard deviation, I mean, for each uncertainty, you are going to fine-tune the problem, okay? And for each uncertainty, I mean, or I can tell you, for each standard deviation, that is the same thing that I say this in normal uncertainty, you are going to do n big optimizations. And in the paper, we found that 100 or even 50 optimizations for each of these normal uncertainty is enough for linear problems, okay? So this is the amount required, actually. So why to fine-tune the target-rich attributes, okay? So why do we fine-tune the normal distribution, and why we choose to fine-tune it? I think that this is the most important question. Because life is normally distributed, okay? The central limit theorem states that the distribution of sample means approximates a normal distribution as the sample size gets larger, and regardless of the population's distribution. So everything in life is normal distribution in all areas. So what is the limitation of the problem? The problem must be convex, and the objective function must be monotonic for all normal uncertainties, okay? This is very important, and it cannot be used to non-convex problems yet. So this is a drawback of the problem. We'll talk about it further. Okay, the first lemma is that when the problem is monotonic, it will always exist private individual influence. The sum of them is called the superposition principle and configures the overall direction of the problem. The algorithm searches for each of the best individual influence of normal uncertainties. What I mean is that your normal uncertainties and the terms related to it must be an additive uncertainty, not an uncertainty that is multiplying something that will make the problem non-convex. Okay, so X spot is just the best value. If we look here, if we look in this graph right now, we are going to see three different normal distributions, okay? We have an uncertainty X that based on our recent data, we have an average mean, okay? So if we look to the area under this curve, below this curve, we see that the orange curve is the curve that has more chance to randomly generate this desired value, okay? So this is the lemma. So what is X spot? X spot is the value that when we take it and when we substitute it in our model, it's going to generate a solution that is most closer to what we call an ideal solution. This is obvious. We have to have some value that when we substitute it in the model, it will get closer to a specified value, okay? And it's all about probability. So we want X spot. The orange curve has more chance to randomly generate X spot, okay? This is illustrative. And X spot, what is it? There will always exist an uncertainty value leading to a value closer as possible to the target. So in the article, we made more than 20 different optimizations. And here we can see that the more populated range means higher area below the curve, okay? So we used it to 4 different standard deviation values to have a look at it, how it works behind the scenes. And we can see it here that it's true. And higher area towards the X spot means higher chance to generate what we want. So the optimal standard deviation for each normal uncertainty is the one that have the higher chance to get closer to the preset target. It can be mathematically illustrated by this equation and by this equation here. So your optimal fine-tune for each uncertainty J will be the one that you maximize the probability of generating X spot for that uncertainty J, because each uncertainty will have your X spot, okay? Your individual influence for all J's. Okay, here is the algorithm. It's a little bit, it's not easy for a first look, but I will try to summarize it here. We already saw in the graphical abstract what it does. And basically here is that the first step, you are going to calculate your GDOR, or you're going to specify it. Then you are going to use the mathematical formulation to adapt the model, okay? Remember here, your alpha, I think that I don't talk about that, but the alpha here will always multiply a non-normal uncertainty, okay? So in the model, whenever we see a non-normal uncertainty, we are going to substitute the value, the deterministic value of this non-normal uncertainty by its expectance, and we are going to multiply it by the penalty factor. So here we are fine-tuning the sigma, the standard deviation for normal uncertainties, and we are fine-tuning the penalty factor, okay, at the same time, okay? So you are going to perform n-big optimizations based on your RRT data for each normal uncertainty, okay? And you are going to fix all other values, and you're going to fine-tune each uncertainty per time, okay? You're not going to do it just at once, okay? You are going to optimize once per time, okay? Once per instance. So it's basically what it does here. you're going to set different values for sigma. I set 4 in the previous example here. But in real case problems, you can set, if you have a supercomputer, a cluster, you can set from 2 to 20, for example, you can set 1,000 points. Okay. But as I didn't have a supercomputer and my time was very small, I didn't have the chance to do it. So, okay, so here you have to set different values for sigma for each J uncertainty, normal uncertainty, and you're going to perform n big optimizations for each sigma, and you're going to, after the final, you're going to calculate and store the relative regret, and after the end of each optimization, okay? You're going to ask yourself, were the optimizations robust according to the preset trade-off risk? If the solution is feasible, then no, the algorithm know when it's feasible and not infeasible. Then you will go back here, and then you're going to vary the value of alpha again. Okay, you're going to do it in a nested loop in your algorithm to be more computationally language. Okay, so this is what it does. So it's a loop here. If you have, for example, n non-normal uncertainties, it's going to be n loops, nested loops. Okay, and or you can just think about what I said to you. You can use your own subjectivity, okay, to make you to follow your algorithm. So this is very flexible. Okay, if yes, you are going to calculate your average relative regret for all your standard deviations, and your tuned sigma of your fine-tuning normal uncertainty is equal to sigma that minimizes the average relative regrets here. It is the same as this thing here, the same thing. Okay. The tuning for selected epsilon j is complete. Now, were all your normal uncertainties already tuned? If no, you back to step 3, and you're going to do this over and over again till the time that everyone is fine-tuned here. And now you're going to do the third step that I talked that in the resume, that you're going to perform some optimizations and calculate the relative regret for each optimization. You're going to pick the one which has the lowest value for your relative regret for decision making. Okay. Okay, so the restrictions, limitations, and axioms. Your objective function cannot reverse the given order. It must be monotonic within the active convex region. I mean, it can be non-monotonic out of your domain, okay? But in your domain of optimization, it must be monotonic, okay? The normal uncertainties are addressed to parameters that can be manipulated in the practice within bounds or are normally distributed. It is very important because answering the question I did before, I asked why to include normal uncertainties in our real life problem, because actually we have the limit theorem that I talked about, but we have the capability of the power to choose some values for parameters. And how can we choose it? The machine will decide through this algorithm. Okay, but because if we have a heuristic decision of what value we can put to this parameter, it's hard that we first hit the point that will give the solution closer to ideality. Okay, so here the machine decide it's a best way to make the problem more efficient. Okay, and if it is not normally distributed, something in life will be normally distributed. If there is not normally distributed, you just say that, okay, I'm going to put it to be normally distributed because I have the power to manipulate it within bounds. That's basically that. So, And this is an example of why we need monotonicity. Because if we don't have monotonicity, what's going to happen is that we are going to have multiple values of X spot that gives our ideal solution, or that gets closer to it. Because if I take this ideal solution, put it here, actually my objective function will not lead to the value, but will get closer to it. And this is what we want. But we don't have, we don't actually, we can't have multiple values of X spot. Okay? We can't have. So in this research paper, it's called Fine-Tuning Robust Optimization, Attaining Robustness, Targeting Ideality. Here I prove that for linear problems, n big equal to 50 is enough. Please see the paper above. Here I discuss how to apply it to linear and nonlinear applications in real life. And it have a very deeply discussion than I'm doing here. Okay, so how to use it in practical applications in real life, okay? You're going to have to ask yourself, what do you want to design or find the best value or values to determine the best decision making, okay? All models in real life will have a best configuration that leads to a desired target trend, okay? So this is important. So our design constructor is the mathematical formulation. You just have to know how you're going to address each one of them to your problem. Your decision variables, your normal uncertainties, vectors, your deterministic parameters that generally you don't have the chance to manipulate their values, because you can have some parameters that are scarce. It's not within bounds. You have your penalty factors, and you have your parameters that are uncertainties that are following non-normal distributions. Okay, and for how to apply to examples such as design, optimization, process control, planning, supply chain planning, I mean, and other kind of planning, and even portfolio optimization, please see the article. And in my master's degree, I did a case study for an Argon supply chain planning. It basically comprises 6 air separation units, production plants, and it have 84 customers. Okay, the time horizon is 30 days, and this is based on this article here, this model that was published this year. Okay. I'm talking about the uncertainties that I gave to the problem. The first uncertainty that was based on data was the electricity price. And based on the data that was given to me, it had an exponential distribution, okay? So, and the other uncertainty is the customer argon demand that follows a normal distribution, and it's an additive uncertainty in the problem, okay? I just said that it is normal distribution because I have the power to manipulate its value within bounds. Okay. Okay, here I can have this power to manipulate it because the customers have its own inventory. Each customer will have its own inventory. Okay, but it must be within bounds. It means that you cannot lack product and you cannot overcharge your inventory, okay? So just to have an observation here, observing monotonicity, the y-axis is the normalized objective function of the problem, and the x-axis is the normalized electricity price, okay? Here we can see the monotonicity, and we can see the monotonicity here for the general demand, okay, for the customers. Basically, the objective function, it's respect to the driven miles and the electricity used, the amount of it used. Here we have this term. It is a MILP problem, okay, mixed integer linear programming. We have this steady state production cost, okay, this term. This term, it is the plant's initialization cost and this term is the plant's shutdown cost. This term here is the argon transportation cost from plant to plant, the truck leaving in one plant and going to another plant. And here is the argon transportation cost for the transportation between plant and customer and customer and customer. Okay, here to use this framework and to naturally increase the robustness of the problem, I added a constraint to the original model, forcing to have more robust results. Okay, this constraint here actually forces an upper bound for the daily production in all plants. Okay, this constraint is capable of relaxing the production problem and thus increasing robustness by precluding overcharged daily production. It's basically what it is doing. To use the framework, whenever we have a non-normal distribution, we just multiply it by the penalty factor, okay? And we are going to fine-tune the penalty factor in our model. The default value is equal to 1 if you want to have a more realistic problem without the need to reshape your problem, okay? Okay, the demand constraint. This is the argon mass balance, customer inventory. Here we have your additive uncertainty here. This is the inventory balance, okay? And the results of the framework in the argon supply chain was the following. We can see that I used the three different values for the standard deviation because this is computationally cost. This is computationally expensive. I'll talk about it. And it was performed 50 Monte Carlo simulation optimizations for each standard deviation. So in this case, I did 150 optimizations in total. And here, for a specified value of 75% of the nominal value, which is masked here, we got that. And for this preset trade-off, specified preset trade-off risk, we got an improvement in the objective function value of almost 14%. And the fine-tuned value for the sigma was 10% of the average RRT. Here, the same thing, and what I just changed, the optimizations were the same. I just changed the target ideal here. Okay, and we see that when the target ideal is changed, our result changes. Okay, so and if we see in this table here, because this is an stochastic method, not necessarily increasing the preset trade-off risk will increase the objective function value. And this is very important because, again, this is a stochastic method, okay? The computer used was this one that I'm presenting here for you. Intel Core i5, 8 gigabytes memory RAM, and operational system of 64 bits. The software used was the GAMS, this version, and the solver was the Simplex. Okay, each optimization, it's a really big problem. Each optimization have more than 1 million constraints and 1 million variables. The time for doing this fine-tuning was 25 days in this humble computer. It's about 600 hours, and also including feasible optimizations that they typically takes more time than the feasible optimizations. Some future options for this is that it is yet not applicable to non-convex problems, and we have to answer this question: what is the point between creating an improvement and remain the original aspects of the framework? Another question is, complicated tumor can give better results. Is it worthy? The number 4 is penalty factor calculation method to decrease the optimization time. It is important to create this method because if you create this method, you cannot need to vary it into a nested loops, because this is the great computational time problem for this methodology. Okay, And the number 5 is the integration with neural networks in the algorithm. Is it worthy? How can you make it to improve the method? Some drawbacks of the problem. Not indicated for dynamic optimization if there are so many variables or have a small time window for optimization. One must test the time using simulation. The more rigorous the preset criteria are, the bigger are the computational time. If the preset target changes, you must fine-tune again. Current computation expensive for some real-world problems. Not a problem if using 32 gigabytes RAM memory with at least 14 cores in the processor with this frequency. What I recommend is that you use it in a minimum recommended system of 32 gigabytes RAM with Intel Core i9. So conclusions to remember the importance of this work. So here we first avoid transforming a linear problem in a nonlinear one, okay? The second is that we control robustness as you want. You specify your trade-off risk. It is a target-rich oriented, better results than deterministic optimizations. You can apply it to linear and nonlinear applications, but again, it must be convex. You have some space for risk decisions if wanted. It is a data-driven optimization. You can use it for short, middle, or long run. And it will, of course, give you more realistic planning. And 7, it precludes ambiguity. And that's it. Thank you. Any question about the...
Thank you very much. I am turn off the recording and then we can start the discussion of your work.
Okay, thank you very much.